Hello and welcome to the Maths Matrix. My name's Rebecca and it is hot here in the UK this afternoon. I've been for a quick walk, but being such a pale girl I have to be careful not to burn. I burn really easily. So I thought I'd come in here where it's cool for a bit and have a look at the second part of that paper from 1950. I really enjoyed doing the first part, but the video was getting quite long. I don't know whether I'll upload this second part or not, but I did say that I'd be looking at the paper anyway for my own enjoyment, so I thought I might as well film it and I might go ahead and upload it. Alright, so in part 1 of the video we looked at questions 1 to 5, so we'll start now at question 6. If you want to try the question for yourself, just hit pause so that you can see it on the screen. For those of you who aren't going to try it yourself, it says simplify and gives 2 algebraic fractions that need to be simplified. And then in part 2, it says a man cycles A miles from A to B at an average speed of X miles per hour. He returns from B to A at an average speed of Y miles per hour. Find the total time taken and show that his average speed for the whole journey is 2xy over X plus Y miles per hour. If I have a look at those algebraic fractions first, I'll just put the paper to one side so I can write. So we have, for 6 part 1, x over x squared minus x minus 2 minus 4 over x squared plus 2x minus 8. Now normally to simplify algebraic fractions, you will put them over a common denominator straight away. Sometimes teachers tell you to draw a bow on it to do that, and you multiply the bits that are joined by the bow. Again, I'll cover this in later algebra videos, but this is what I'd call a back-end algebra question. However, the denominators here are quite complicated, more complicated than you'd usually get on algebraic fractions now. So the first thing that I'm actually going to do in this case is factorise each of those denominators. So I'm going to leave the top as x, and I'm going to factorise that quadratic at the bottom to x minus 2, x plus 1. I'm also going to factorise the other denominator. If you want to try it for yourself, then hit pause now because I'm going to factorise it quite quickly. And that factorises to x plus 4, x minus 2. Okay. What I'm now going to do is I'm going to do the thing where you draw the bow and multiply bits that are connected by lines. That's a quick shortcut way of bringing 2 fractions together into one big fraction. So I'm going to multiply x by that denominator there, and at the moment I'm not going to expand any brackets. I'm just going to leave things together in brackets next to each other like that. I'm going to multiply those bits, again without actually expanding the brackets. And then that will all come together over a common denominator of x minus 2, x plus 1, lots of x plus 4, x minus 2. So if I had multiplied those denominators, I've multiplied them in that form instead, so it looks different, but it is the same thing. What I can now notice is that each of these have an x minus 2 in that can be crossed out. So both terms on top and the big chunk term underneath, they all have an x minus 2. So I'm just going to cross an x minus 2 off each of those. That'll then give me x squared plus 4x on top minus 4x minus 4, so I'm expanding these top brackets now, over x plus 1, lots of x plus 4, lots of x minus 2. That then simplifies to x squared minus 4. Oh, didn't need that bracket. Over x plus 1, x plus 4, x minus 2. And that top part is now a difference of two squares scenario. So I can now factorise that top part as x plus 2, x minus 2, still over x plus 1, x plus 4, x minus 2. And again, I have matching brackets that can be crossed out. And that'll give me an overall answer of x plus 2 over x plus 1, x plus 4. And so to refresh your memory, 6 part 2 was about the man cycling A miles from A to B and then cycling back from B to A. So what we have here is a 2-stage journey. So for part 1, we've got the distance is A and the speed is x. Well, if speed, distance and time go into a relationship triangle like that, then time equals distance over speed. So when we know two things in a speed, distance, time scenario, that is always telling us that we need to find the third thing. Even if the question doesn't say, here are two things, find the third, that is usually what the crux of the question is. So for part 1 of the journey, the time will equal A over x. For part 2 of the journey, the distance is still A because we're told that he returns from B to A, so obviously the distance hasn't changed, but this time the speed is y miles per hour. So in this scenario, the time will equal A over y. Then it says find the total time taken. So the total time will equal A over x plus A over y. As part 1 was to do with combining two fractions, I'm going to put the combined version in as well. So I don't know at the moment whether I'll be using the 2 separate fractions version or the 1 single fractions version. But again, if I was to draw that bow on so that I could gather these 2 fractions together as 1 single fraction, I'd end up with AY plus AX over XY. And I'm going to factorise that as well for good measure as A. I'm also going to switch the order, x plus y, just because alphabetical order is usually how things are presented. So all these 3 things, although they look different, all represent the same thing, and I don't know which of those 3 forms I'm going to need yet, so I've put them all down. So show that his average speed for the whole journey. I'll just bob across to the other side now. So for the whole journey, we now know that the distance would be 2a. And we know that the time is one of these 3 things here. I'm going to go with the bottom version. This is a good exam tip, really. Very often in an exam, if a question is broken down into 2 seemingly unrelated parts, it's because somehow the first part of the question is going to provide some sort of clue as to how the second part of the question needs to be done. Because the first part of the question was telling us to join 2 fractions together and involved quite a bit of factorising, I'm going to assume that in this second part of the question, they want the joined together factorised version for time. So that's what I'm going with. So now we've got a speed equals distance over time scenario again. So now what we need to do is we need to do 2a over ax plus y over xy. Once again, GCSE students, what did I say during fractions? I said if they don't test your ability to divide fractions explicitly, they'll test it somewhere. Here, we're being asked to divide one thing by a fraction. A-level students, you will be tested on this somewhere as well, I'm sure, and in an algebraic way so that you can't just stick it in your calculators. So that will be 2a divided by ax plus y over xy, which is 2a times xy over ax plus y, which is 2axy over ax plus y. We've got an a on top and an a underneath that can cancel, which gives us 2xy over x plus y, which is what the question said we had to get because it was a show that question. I think that is harder than a modern day GCSE question. However, the concept still comes up on modern day GCSE questions. If on a speed, distance, time question, your journey is split into 2 stages, then you always have to do a part 1 where you write down the 2 things that they give you and find the 3rd thing. Separate to that, for part 2, you then write down the 2 things that they give you and find the 3rd thing. And then the question becomes about combining that information in some way using the total distance, the total time to find the average speed. I think on a modern day GCSE, they'd usually give a 2-stage speed, distance, time question in plain number. Or if they did use some algebra, I think it would be simpler algebra. So I do think this is more difficult than what you would expect to find on modern GCSEs. Question 7, again it's there on the screen if you want to have a try. My drawings are going to be quite rough because I'm not using graph paper, I'm just using plain paper. GCSE students, you should be able to do the drawing part of this. I'm not convinced you'll be able to do the second part of the question. A-level students, you should be able to do the whole lot. Please remember this was a non-calculator paper and this could still be on a non-calculator paper nowadays, so we'll try and do it without a calculator. So it says, with the same axes and scales, draw the graphs of y equals 7 over 4 plus 3x minus x squared and 4y equals x plus 3 for values of x from -1 to 4. Show that the values of x where the graphs intersect are the roots of 4x squared minus 11x minus 4 equals 0, and hence find approximate roots of this equation. All right? Again, I'll put the paper to one side so I can write. So we have y equals 7 over 4 plus 3x minus x squared. When we're drawing graphs, when we're plotting them accurately, we always need a little table of x against y. So they're telling us to use x from -1 to 4. We need to do y equals 7 over 4 plus 3 lots of -1 minus -1 squared, which will equal 7 over 4 minus 3. -1 squared means -1 times itself, which means +1, okay? So if you ever ask your calculator to square a negative number, you must put brackets around it, or else your calculator thinks you're asking something else entirely. So if we square -1, we get +1, but we're then minusing +1 to give -1 overall, which will give us 7 over 4 minus 4, which is, shall I put it in a decimal? there's two ways now you can do this. It's personal choice, really. As a decimal, that's 1 3/4, which is 1.75 minus 4. If you wanted to do it using fractions, we've got 7/4 minus 4/1, which would be 7/4 minus 16/4, which would be minus 9/4, which would be minus 2 1/4, which would be minus 2.25, which is the same as what we get there. So I'll go with minus 2.25. 0, I can do that in my head. 7/4, well, 3 zeros are 0, 0 squared is 0, so that's just going to be 7/4, which is 1.75 as a decimal. Doesn't matter whether you use fractions or decimals, but because we have to plot this on a graph, I feel like it'll be easier to do if we're using decimals. Move you across here while I do the next one. So we have y equals 7/4 plus 3 lots of 1 minus 1 squared, which is 7/4 plus 3 minus 1, which is 7/4 plus 2, which is 1.75, 2.75, 3.75. We have y equals 7/4 plus 3 lots of 2 minus 2 squared, which is 7/4 plus 6 minus 4, which is 7/4 plus 2, which will be the same 3.75 as before. Where to do it so that I won't run out of room and you can see. I'll do it over here. Y equals 7/4 plus 3 lots of 3 minus 3 squared, which is 7/4 plus 9 minus 9, which is just 7/4, which is 1.75. And y equals 7/4 plus 3 lots of 4 minus 4 squared, which is 7/4 plus 12 minus 16, which is 7/4 minus 4, which is the same as up there, which is minus 2.25. All right. So my table of x against y values for the first part is going to look like that. I'll just box it off so I can find it more quickly after. So the next thing I have to draw is 4y equals x plus 3, which becomes y equals x plus 3 all over 4, because I need to know how to get y from x. So I need to make y the subject, in other words. So I'll draw my x against y table there as well. And it wants it from -1 through to 4 again. Right, I'm going to do some of these in my head without doing all this writing because I've only got a tiny bit of room left. If x is -1, then -1 plus 3 is positive 2, and positive 2 over 4 cancels down to positive 1/2, which is 0.5. 0 plus 3 is 3, divided by 4 is 3/4, which is 0.75. 1 plus 3 is 4, divided by 4 is 1. 2 plus 3 is 5, divided by 4 is 5/4, which is 1.25. It doesn't matter if it takes you longer to do this. I'm just going to put commas between these. And I'm going to cheat the rest because I know that they're going up in 0.25s. I know that from y equals mx plus c work. But if you didn't know that in an exam, or if you wanted to be careful, you would check each value properly. I just know that they're going up in 0.25s. So that's my x against y table for the second graph. We need an x-axis that runs from -1 to 4. So we've got -1, 0, 1, 2, 3, 4. And we need to be 4 high and down to -2.5. So our first point in this table here is -1, -2.25, which would be sort of there-ish. Then I'd have 0, 1.75, and I'd have 1, 3.75, and 2, 3.75, and 3, 1.75, and 4, -2.25. About there-ish. I might do this in pencil. You should always draw graphs in pencil, by the way. Again, it's just because I'm not on proper graph paper, I'm not in a real exam. But I am going to join them in pencil because I feel like I might make a bit of a mess of it. So what we have there, I've obviously messed up my scales a bit. What we have there is a squared graph. A-level students, you should have recognised all along that this was going to be an N-shaped graph because of the -x². GCSE students, it's a very common question on exams that they'll give you something like just that part and ask you to fill in an x against y table and then draw it. Always join your points with a smooth curve. And if you have two like this that are on the same level as each other, it doesn't mean that you flatten off. It means that you make like a peak and come back down again, because usually in the case where you have this shape, it's because there's a squared going on. So you'll have a graph that's either that shape or a graph that's that shape. So you'll get marked down if you flatten off, and you'll get marked down if you join with straight lines. So a smooth curve and a nice peak or a nice dip. I then need to plot these other points. So I've got -1, 0.5. I've got 0, 0.75. I've got 1, 1. I've got 2, 1.25. I've got 3, 1.5, which will be kind of just slightly under that one, and 4, 1.75. This is where I've not used a proper scale. It's going to affect the answers. This second graph here is a straight line graph, so it would go kind of like that. This is not exact though, because I shouldn't actually have a point of intersection there. It doesn't matter if you don't know why, but I shouldn't have a point of intersection quite there. So that's my fault, because I've not done it properly on nice neat squares. I've just kind of guessed the scale. But that is the drawing part of the question done. It then says, show that the values of x where the graphs intersect are the roots of that thing there. You do meet this very occasionally towards the very back of GCSE papers, and you meet it all the time at A level in your coordinate geometry type work. Intersection means simultaneous equations. Points of intersection occur at the solutions to simultaneous equations. So what we're now being asked to do is solve those simultaneous equations. And because there's a squared in that one and not in this one, these are quadratic simultaneous equations. GCSE students who are hoping for one of the higher grades, I cannot recommend strongly enough that you learn how to do quadratic simultaneous equations. Again, I'll definitely be covering them in a later video. So we have y equals 7/4 plus 3x minus x squared, and also 4y equals x plus 3. I rearranged that earlier to y equals x plus 3/4. So if y equals that and y equals that, which is what simultaneous equations mean, that both things are true at the same time, I can pick up that chunk and I can put it in place of y there. So if y equals that and y equals that, then it follows that x plus 3/4 equals 7/4 plus 3x minus x squared. I'm now going to get rid of these fractions by timesing out by 4 to give x plus 3 equals 7 plus 12x minus 4x squared. I'm then going to get everything all on one side. And I'm also going to make the x squared term positive, because if we look at what we're aiming for that which is positive, 4x squared. So I'm going to move that 4x squared over there. In other words, I'm adding 4x squared to both sides to give 4x squared plus x plus 3 equals 7 plus 12x. We're then going to move the 12x, 4x squared minus 11x plus 3 equals 7. And I'm going to move the 7, 4x squared minus 11x minus 4 equals 0. Just like they said. Okay, so we've now shown what they wanted us to show because we have derived that equation. Because it says approximate roots, I'm going to use the quadratic formula, I think. -16. Yeah, I don't think this will factorise, so I'm going to use the quadratic formula. So x equals negative b plus minus the square root of b squared minus 4ac all over 2a, where a equals 4, b equals minus 11, c equals minus 4. I think I'm going to run out of room. In fact, I am. I'm going to come over here and do it sideways, which again, I wouldn't do in an exam. So x equals, now b is negative 11, so negative b will be 11, plus minus the square root of negative 11 squared minus 4 lots of a, lots of c, all over 2 lots of a. I would recommend that you always write it out, the formula, and then in full like that, rather than trying to do it as you're going along. I think it's very easy to make mistakes if you try and do it at the same time as writing it. So I always say just write the formula, then sub the numbers in the right spaces without doing anything at all to them, really. In fact, sometimes I would even have students write negative 11 rather than make it positive straight away there, because then it's so much easier when you're looking at it to work it out and not make mistakes. So that's 11 plus minus the square root of 121. Now, I say to people, times the numbers first and then work out the sign. So 4 4s are 16, times 4 again is 64. It doesn't matter if you don't know that as quickly as me. I only know it from all the laws of indices work I have to do. And then 2 negatives multiply to make a positive, and that's over 8. Then you can bring these bits together. So that's going to be 11 plus minus the square root of 185 over 8. Now, if you remember on question 5 from part 1 of the video, they were asked to find a cube root using tables, and I said that that didn't mean times tables. It meant that table of logarithms that they got provided with. The square root of 185 isn't a whole number. It's not a nice, neat integer. So they would have had to look that up, I presume, in their table of logarithms. And then when they'd looked it up in their table of logarithms and got an approximate answer, I assume, then they would have added it to 11 manually, and then they would have divided it by 8 manually to get approximate values. Nowadays, if you were on a non-calculator paper, they'd probably say leaving your answer in surd form, which would be just leaving it like this. Or more likely is that it would be on a calculator paper so that you could go ahead and get the solutions. But what I'm going to do is I'm just going to leave it there so that those would be those would only be the x values though, wouldn't they? And did it say it wanted the y coordinates as well? Oh no. approximate roots means it just wants the x values of where those two things intersect. It doesn't want the y values as well. So I have my x solutions there now because there's the positive version and the minus version in that plus minus. And I'm just going to leave mine like that because I don't have logarithm tables and they didn't have a calculator. Right, question 8. GCSE students, you won't be able to do this because this is not on the GCSE syllabus anymore. So it was on the O Level syllabus, which was what your age did in 1950, but it's not on anymore. It is, however, on A Levels, so I will go through it, and A Level students, you should be able to do it, I think. So we are told that the first term of an arithmetic progression is minus 12. So we have a equals minus 12. And we're told that the ninth term is 0. I'm going to put un equals 0. You might not use the un notation. I think some of you sometimes use something different, but the ninth term, in fact, I'm just going to put ninth term. Then it doesn't matter what you use, does it? Ninth term is 0. So it says find the common difference, first of all. So part A says find the common difference. Well, we have nth term equals A plus n minus 1 d. The ninth term is 0, which is minus 12 plus, well, if n is 9, then 9 minus 1 is 8d. So we have 8d equals 12. So we have d equals 12 over 8, which is 3 over 2, which is 1.5. I now need to find the number of terms whose sum is minus 45. I did it there with positive 45, then tried to correct it afterwards, and I just thought, no, start it again. So Sn equals a half n 2a plus n minus 1 d. You get given that in your formula book. So minus 45 equals a half n. We know now that a is minus 12, so that's negative 24, that 2a part, plus n minus 1. And for d, I'm going to go back to using a fraction. So instead of using the 1.5, I'm going to use 3 over 2, just because it'll be easier in the algebra. So minus 45 equals a half n minus 24 plus 3 over 2n minus 3 over 2. Minus 45 equals minus 12n plus 3 over 4n squared minus 3 over 4n. It's incredibly hard, I'm finding, to talk and do at the same time. That's what went wrong over here. I was talking and I was trying so hard to concentrate as I was talking and to stop talking in order to concentrate, but I just find it really hard to do both at once. So I'm sorry about that. Let me just check it now. Right. So I'm just going to times out by that 4. You don't have to, you can do something else first if you like, but I want to get rid of those fractions. To give me minus 180 equals minus 48n plus 3n squared minus 3n. And that's going to give me minus 180 equals minus 48, 49, 50, 51, minus 51n plus 3n squared, which is 3n squared minus 51n plus 180 equals 0. Each of those bits will now divide by 3. GCSE students, this is now a quadratic, so you can solve quadratics. So from this point you can join in. But before I start to solve it, I'm going to divide each term by 3 to make it a little bit easier for myself. So n squared, 3 into 5 goes 1. minus 17n plus 60 equals 0 is the quadratic that I'm going to solve. That will factorise because I know that n needs to be a whole number because it's to do with a number of terms. And if the solution is a whole number, then that usually means, well, that always means that the thing will factorise. So we're going to pick n minus 5, n minus 12 for the factorised version, so that n equals 5 or n equals 12. Usually, A-level people, when you're asked for the number of terms that sums to something, you just end up with one n value. Here we end up with two n values, and I thought at first that we were going to have to pick either or, but I've just checked longhand, and the first 5 terms sum to minus 45, and the next 7 terms sum to 0. So actually, you'd get a sum of minus 45 at both n equals 5 and n equals 12. So there were 2 answers in this case. Looking at part B, it says insert 3 positive terms between 10,000 and 256 so that the first 5 terms are in geometric progression. Again, GCSE students, you won't be able to do this. What's implied when it says insert 3 between so that the first 5 terms are in geometric progression is that we have first term 10,000 and fifth term 256, and it's the second, third and fourth terms that we need to find. The geometric sequence nth term equals AR to the n minus 1. A is 10,000 because the first term is 10,000. So we have A equals 10,000. And at the fifth term, we have 256 equals 10,000. R, which we don't know, to the power 4. So R to the 4 equals 256 over 10,000. We could then cancel this fraction down. I've just cheated it on a calculator because, again, this video is getting really long and I still have 2 more questions to do, but cancelling that down is straightforward enough. You just have to put the legwork in to get 16 over 625. Both of those are square numbers, so we can root the whole thing to give our squared equals 4 over 25. I thought it was, but I don't want to make any more stupid mistakes like I did in part 1. So r squared is 4 over 25, and again, both of those are square numbers, so r equals 2/5. So my second term is going to be 10,000 times 2/5 or times 0.4, which is going to be 4,000. My third term is going to be 0.4 times that, so that's going to be 4,000 times 0.4, which is going to be 1,600. And my fourth term is going to be 1,600 times 0.4, which is 640. And then we can check that by timesing 640 by 0.4 and seeing if we do get that fifth term of 256. And I think that those are both still very typical of what you'd get on a modern day A level, but not a modern day GCSE. So we can do that question. Question 9. It's there on the screen if you want to hit pause and have a go at it. If not, it says a point P is outside a circle with centre O and of radius 4.5 centimetres. A line PAB intersects the circle in A and B. The line PO intersects the circle in X. PA equals 4 centimetres and PX equals 3 centimetres. Calculate the length of AB and the angles AOB and APO. And they were given no picture to help them with that, so we are going to have to try and draw one. I'm surprised to see centimetres on the paper actually, because looking ahead to question 10 has units in inches, and I wasn't aware that they had centimetres in the UK in 1950, so that surprises me. So we have a circle with centre O and radius 4.5 centimetres. So let's just put a random point P outside the circle. And then it says PAB intersects the circle in A and B. Now it doesn't say that that line PAB goes through the centre, so I'm purposely going to draw it not going through the centre, because later on we're told some information about PO which will be through the centre. So I don't think it matters which way round A and B go, so I'll have A there because it's the first point that P would encounter, and B there. Then the line PO, so that tells us that there's also a line joining P and O. So that's the line PO, and that intersects the circle in X, which means that that point there, that bit there, is X. PA equals 4 centimetres and PX equals 3 centimetres. Calculate the length of AB, the angles AOB and APO. So they want us to find this length here. I'll just embolden it slightly. So they want to know how long is that bit. They want the size of that angle there. And they want the size of APO, which is that angle there. Wow, okay. Right, I've just taken some time to have a proper look at this diagram while I'm not simultaneously talking to you, and I have figured out a way that the question can be done, but I don't know if it's the same way that they would have done it in 1950 on the actual paper. If we imagine a line running from A to O, that's also going to be a radius. So the radius of the circle is 4.5, and that means that because A is on the circumference and O is the centre, AO is also 4.5 centimetres. So if I look just at the triangle APO, what I have is that AP is 4 centimetres because the question said so. AO is 4.5 centimetres because it's a diameter, and PO is made up of 3 centimetres from P to X plus 4.5 centimetres diameter, so altogether the line PO is 7.5 centimetres. One of the things that the question wants us to find, and this is why I'm not sure that I'm doing it in the same way that it would have been done in 1950, it wants us to find AB, AOB and APO, which is that angle there. So APO is that part there. Usually nowadays in an exam, if it says find X, Y and Z, usually you go in order and you find X first, and then you find Y after, and then you find Z. I don't know if the way this question's worded means that they specifically thought you could find AB first, and then you had to find AOB, and then you had to find APO. or whether you could find them in any order. They wouldn't mark you down, I'm sure, for finding them in the wrong order, but it could be that it was easiest to find AB first. But I've had a look and I cannot think of a way to get to AB before finding some of the other information. So I'm going to find APO first. We've got a non-right angle triangle where we know 3 sides and want an angle. So that's going to be the cosine rule. So the cosine rule for angles is cos A equals b squared plus c squared minus a squared over 2bc. Don't worry if you're quite early on to your GCSE course and you haven't learned this yet, but A Level students, you should be familiar with this and you should be able to do this question, this part of the question without any more prompting now. I would have 7.5 squared plus 4 squared minus 4.5 squared, because the thing taken away at the end in the cos A rule is the thing opposite the angle. So I'm trying to find this angle, so the side that I subtract must be its opposite, which is 4.5, and the order of the 7.5 and the 4 don't actually matter. Now, in 1950, again, because this was a 3-hour exam, if they were using the cosine rule, they'd have to work all these bits out without a calculator. So to find 7.5 squared, they'd have to do 75 times 75 and then stick the decimal point in. So they'd have to say 5 5s are 25, 5 7s are 35, 36, 37, block off with a naught, 7 5s are 35. 7 7s are 49, 50, 51, 52. Then they'd have to add those up. And then they'd have to put the decimal point back in at the end. So 1 dp going in times by another 1 dp would produce an answer to 2 dp. So in the 1950s, they would have had to do that longhand. To save time, again, because I don't want to spend 3 hours on the paper, I'm not going to do it longhand because I'm confident that I know how to multiply numbers without a calculator. We would now say P equals the inverse cos of 13 15ths. I don't know why I've written 50 there. It was 15 that I should have written. We would now just stick that into the calculator. In the old days, they had things called trigonometric tables, which, much like logarithm tables, was just a big table of sine, coses and tans, and presumably inverse sine, coses and tans. So I haven't got any trigonometric tables, so I'm going to just have to use a calculator, and that produces 29.9264. So I'll say 29.9 degrees to 1 dp. Okay, so the first answer that I have is APO equals 29.9 degrees. It doesn't say what degree of accuracy they wanted it to, so I'll go with 3 sig fig. They now want this bit here and this length here. I'm going to use the sine rule next to find this angle here. Because if I can find this angle here, then I can deduce that angle there. And on the basis that this triangle is isosceles, if I know that angle there, then I know that angle there. And if I know those angles, then I know that angle, which gets me to the next key piece of information that they want. So I'm now going to use the sine rule again at this triangle here. I'm thinking just of this triangle for now, to find this here, which I'll just call x. Okay, so I'm going to say sine x over its opposite equals sine of 29.926 over its opposite, which would be 4.5. So that sine x equals sine 29.926 over 4.5 times 7.5. Now again, they would have had to refer to their trig tables which we don't have, so I'm going to have to do it on a calculator. So that's sine x, so x would equal the inverse sine of 0.8314. And the answer to that part is 56.251, which I'll work with 2dp, I think, because again, I'm going to need that to do some other things. So I'll call that 56.25. So that bit there, that can't be right though. Right, major confusion there from me for a second, because we did this sine work down this side to get an answer of 56.25. But of course, when I came to label it in the triangle as 56.25 and looked at what was supposed to be on the other side, I realised that that is more than 90 degrees and that is less than 90 degrees, so that can't possibly be 56.25. So 56.25 is our principal value, and by the symmetries of our sine curve, if 56.25 is our principal value there, then the other possibility would have been 180 take 56.25. So that part there, don't worry if that's a bit confusing, GCSE students. It's more an A Level thing really, where you have to use symmetries and you have to find other alternatives when the principal value isn't the value. So actually, it's this part here that's 56.25, because that there is 180 minus 56.25. So the actual numerical value of that angle there isn't so important, because it's 180 minus that, and then by angles on a straight line, that bit is 180 minus that, which takes us back to 56.25. So angle OAB is 56.25. Because they're both radiuses or radii, that is also 56.25. So if that's 56.25 and that's 56.25 and all the angles in a triangle add up to 180 degrees, that must be 67.5 degrees. It doesn't matter that it looks more than 90 degrees, because this was all just a sketch in the first place. So that is 67.5 degrees. So now we've found one of the other bits of information they wanted, which is the AOB equals 67.5 degrees. And I'll give that again to 3SF. We then need to find AB, and I'm really going to struggle for space here. So we have ourselves 67.5 degrees, 4.5 centimetres, 4.5 centimetres, like that, okay? And we're being asked to find that length AB. If I drop a perpendicular there, then that will make 90 degrees. So what I'll then have is a right-angled triangle with 4.5 centimetres, 33.75 degrees, and an unknown length, which will be half of AB. I can then use normal SOHCAHTOA to find that, which I'll call X. So I want the opposite, so I know the hypotenuse and the angle. I want the opposite, so I'm going to use sine. So X equals sine 33.75 times 4.5 equals 2.5, 0, 0, dot, dot, dot. So that is 2.5, which was half of AB. So AB equals 5 centimetres. All right, I think that was a very hard question. So I've either missed something obvious. Looking at what a nice neat number 5 is for the AB part, I feel like they probably did have to get there first. And yet I can't really think how they would have done it. I can't think what information I've missed, what I'm not seeing in this picture that would have enabled me to get AB as 5 centimetres more quickly, which might well then have made the rest of the question very much quicker and easier. But nevertheless, even after you'd found AB, if you found that first, you would still have to do trigonometry to find the angles, and that would have been a case of looking things up in trig tables. So question 10 is there if you want to try it. Once again, I will attempt to draw this scenario. So we've got AB above DC. AB is 6 inches. AD is 4 inches. The plate is turned through 30 degrees in its own plane about A into a new position so that B dash is higher than B. This thing is going to be rotated 30 degrees upwards or 30 degrees anti-clockwise about A. So the position of A will remain unchanged. I think I'd definitely better switch to pencil now. We're going to have the same 4x6 rectangle. Like that, so that B dash is there, D dash is there, and C dash is there. So they just mean the images of B, C and D. So that is also 6 inches and that is 4 inches. Obviously, because it's rectangles, all these angles here are 90 degrees. I don't want to label them all up in case it gets cluttered, but the inference is that they're all 90-degree angles. That is 30 degrees. Calculate, oh my lord, calculate B dash B, which is that, and B dash D, which is that. What we've got, if we ignore all of the bottom part, we've got an isosceles triangle, A, B, B dash, because A to B was 6 inches, and after the transformation has happened, A to B dash will still be 6 inches, and the rotation was through 30 degrees. And we're being asked for the length there. So what we've got ourselves is a cosine rule scenario. I know that looks like it might be a right angle, but we can't assume. There's no reason to assume that that would be a right angle. It's just that the diagram isn't to scale. Sorry, I've just realised it's not on the page properly either. So we need to find that there. So, the general cosine rule is a squared equals b squared plus c squared minus 2bc cos A. And what matters is that it's two sides and the angle between them. So I'm just going to call that x for ease and say x squared equals 6 squared plus 6 squared minus 2 lots of 6, lots of 6, lots of cos 30 degrees. I get 3.1058, which is 1 point. I'll go with 3.11. That would be inches to 3 SF. It's not asked for a particular degree of accuracy. So that there is the B dash B part, 3.11 inches. To find B dash D, which is hard to say, I'm then going to consider the triangle A, B dash D. AB dash is 6 inches, AD is 4 inches. Now what I've got, DAB is made up of the original 90-degree angle that the rectangle was, plus an extra 30 degrees. So that there is 120 degrees. So again, now this is just a standard application of the cos rule, which gives us 8.7177 and so on. So I'll do 8.72 inches to 3 SF. So we have for our final answers, B dash B equals 3.11 inches and B dash D equals 8.72 inches, both to 3 SF. Okay. Overall, I can do this paper if I'm able to use a calculator to do things like the square roots and the trigonometry and the log stuff that we would nowadays use a calculator for. So I don't think, apart from part 2 of question 2, which was where we had to be able to convert yards into miles, that's something I just couldn't do because I didn't know how many yards were in a mile, and I've not bothered to look it up either, so I still don't. But the maths behind the rest of the paper, I understand and think I'm able to do, but I need a calculator for it. So if I was sitting this paper with a calculator, but all the questions phrased like this, then yes, I think I would do all right on it. But if I was forced to sit it in the old-fashioned way with no calculator and just tables of logarithms and trig tables, then I don't think that I would do very well at it. I think it is harder than a modern day GCSE. Question 1 and 2 are still fairly GCSE typical. It's more the units and the wordiness of them that makes them worse. Though as we saw, I messed up the divide spectacularly. But they're similar, maybe a little more challenging. Question 3 part 2 is now A level content and doesn't come up at GCSE. Question 4, not much change really, besides the fact you might not get fractions and that one would be over there. Question 5, not applicable, times have changed. Question 6, I think harder. The same kind of things still come up, but I think that this is harder than what you'd get nowadays. Question 7 would be considered, I think, a challenging example of GCSE. It's still stuff that might come up, but I feel it's, again, perhaps set out a little more difficultly. Question 8, A-level content. Questions 9 and 10. I just think they're harder. Yes, you still get the sine and cosine rules. Yes, you still get things where you have to do isosceles triangles within a circle using the radius. You still have your circle theorems. You still have rotations. But I think the wordiness of these questions, the fact that you're being asked to do so many different things within one question, and the fact that they had no picture to help them, all make them more challenging than you get on a modern day GCSE. So I'd be interested to know what you think. Do you think this is harder than modern day GCSE? Would you have liked SAT exams in 1950, or are you glad that you're sitting them nowadays? A-level students, if you're trying the paper, what do you think? How do you think it compares to the GCSE that you sat? How do you think you'd fare doing this if this was an A-level paper? Let me know your thoughts down below. Alright, I hope you enjoyed doing this and found it useful. If you'd like to see me do any more vintage papers, then just let me know in the comments below. I do have a few more, some from earlier, some from later, and some early GCSEs as well. I enjoy doing things like this, so it would be no bother to film it as I'm doing it and upload some more if that was something that you wanted. Thank you very much for watching. If you did enjoy the video, please consider subscribing or liking, and I will see you next time.